So to go live, going live, going once, going twice. Okay, now we're live. I just need to wait because I have to mute, otherwise it's the double. You can hear things twice. There you go. Perfect. Okay, excellent. Good. So everybody's here, and then we're about to. I usually follow my iPhone is my universal clock that I follow. So by the way, Bert, we are having Stefan is organizing this workshop in September in Venice, yeah. Mm-hmm. So you heard about it?
October in Venice? No, I didn't hear about it yet.
Yeah. What's that? Should be good. Should be good. Okay, so I think we're all here now, and we can start. So I would like to welcome everybody to the last seminar series of the last seminar of 2021 of this online SPICE-SPIN+X seminar series, organized here by the Spin Phenomena Interdisciplinary Center that I lead together with Karen Eversole-Sitte, now W3 professor in Duisburg, and in collaboration with the SPIN+X Collaborative Research Center, led by Martina Schliemann and Burkhard Hillebrands in Kaiserslautern and Matthias Chloe here in Mainz. This is the Zoom live streaming seminar, meaning that you would hear the speaker on the slide, but unfortunately you don't see the rest of the audience, which were about 100 or so. But please, you can write your questions in the Q&A so that everybody can see them. And yeah, other than that, afterwards, once the Q&A starts, I will give you the floor to promote you to panelists if you like to ask the questions directly and participate, or just the audio, whichever one you prefer. And if audio doesn't work, I can also read the question for you. So the speaker today is Bert Koopmans. I always mispronounce your name, sorry. He got his PhD from Göttingen, and he's been now quite a long time as a professor in Eindhoven, and he's well known in the spintronics community, particularly in ultrafast and nanomagnetism and magnetization dynamics community, but also has had a large impact in organic spintronics as well. And is known also for extremely good lectures as well, and very clear ones. Therefore, that's the reason why he's a distinguished lecturer of the Tablet Society. So with that, I'll stop sharing. And I will ask you to go ahead and please share your initial slide and begin whenever you like. And we'll mute ourselves here as well. Okay, that's perfect. Go ahead.
Let me see. You see my slides?
Yeah, everything's perfect. Yeah, go ahead.
Okay, thank you, Yayo, for the kind introduction and the kind invitation. It's a great pleasure being all with you online in actually my last IEEE distinguished lecture of 2 years. And during this presentation, I'd like to discuss with you how these fields of femto-magnetism and spintronics are rapidly meeting. And this is a unique playground for very exciting physics, but we hope also that it might lead to maybe some completely new technology that of integrated magneto-photonics. And I hope that all of that will become clear during my presentation. So, you know, as a distinguished lecturer from IEEE, I have to make a bit of an advertisement about this organization, but I'm pretty well, you're very familiar with it. So you see here a collection of their activities. Actually, I should acknowledge Matthias, from whom I borrowed this slide. And you also see actually that I had the great pleasure and the honor to be distinguished lecturer now in 2 years, together with Matthias, Tim Hughes, and Masashi Shirashi. And if you do not know enough about the organization, there is a website here and you can become a member. So getting back to the topic of the presentation today, I mentioned already these fields of femto-magnetism and spintronics are rapidly meeting. And you see here two iconic cartoons of the two fields. At the left-hand side, you see this amazing work, which was published in 2007 in a group of Theo Rasing and Nijmegen, where they show for the first time that you can really switch a magnetization from up to down using only femtosecond laser pulses. At the right-hand side, you see a typical image from today's spintronics, where it's all about spin orbit torques, etc., and all kind of very sensitive schemes of switching magnetic elements driven by currents. Now, both in this field of femto-magnetism, changing magnetic states at a femtosecond timescale, and in spintronics, it is all about conservation and transfer of angular momentum. Now, not only that, also there turn out to be a lot of hybrid concepts that have shown up, and I will discuss with you a few of them today. Now, as I mentioned before, this is a great playground for exciting physics, but also for potential new technology. And to share with you the vision we have in Eindhoven on this, I have this specific slide where you see how we think that spintronics and photonics can meet really on an integrated photonic platform. What is shown here is data streams of information guided through photonic waveguides. At the intersection with a magnetic strip, you could transfer the information from the photonic domain into the magnetic domain using this process of all optical switching of magnetization. Within the magnetic domain, you could act on it by spintronics means, and finally you could read it out again from the magnetic domain into the photonic domain using magneto-optics. And again, I stress the idea would be to have all of this integrated in a photonic integrated circuit. And for instance, you could think then of photonic racetrack memory. Interestingly, all of these conversions could be done without any high frequency electronic steps. Now, in order to realize these kind of devices, we would need a special materials platform, which would be able to host both the photonic as well as the spintronic tricks. And there we are kind of inspired by developments in spintronics. And you are all familiar probably with these synthetic antiferromagnetic systems, ultra-thin layered materials where you have magnetic ultra-thin films which can be coupled antiferromagnetically, and thereby you can easily tune their magnetic moment. And these kind of materials, when adjacent to heavy metal element thin films, actually host a lot of spin orbit phenomena which are highly relevant for today's spintronics. You see here, for instance, the perpendicular magnetic anisotropy, chiral spin textures, spin hole effect leading to spin orbit torques, and all of this together actually leads to ultra efficient transfer of magnetic information through such a strip driven by electrical current at ultra high velocities. It has been reported already a couple of years ago in Stuart Parkin's group that if you have such a system close to compensation, you can easily get velocities, current-induced domain-wall motion over 500 meters per second. And more recently, it has even been shown to be kilometers per second. Now, this actually is interesting. What's in a number? Well, actually, if you have 5,000 meters per second, and if you would have bits of 50 nanometers, it would give you access to 100 gigahertz data rate. And actually, it brings it really into an interesting domain of technology. Now, before going to the details, I'd like to start with acknowledging all the young researchers in the group in Eindhoven. The top row mostly working on optics and dynamics, and many of them you will see on the forthcoming slides. Also PhD students, postdocs working on related fields. I would acknowledge the collaboration with other PIs in Eindhoven, as well as many international collaborations in some of the European projects which are at the moment are going on. So on my agenda for today is I will starting with a bit more background on this fascinating process of all optical switching of magnetization. Then I will introduce another, I could say, hybrid process, which is the idea that you can generate spin currents just by femtosecond laser pulses. Then I will make the step of integration, where I will show that you can also have the all optical switching in the synthetic antiferromagnets. And finally, I'm going to combine all these concepts in new results on all optical switching in combination with spin currents. And my last slides are reserved to some more insight in recent developments towards the future applications. Now here you see once more this drawing of these experiments, which now are were performed by now approximately 14 years ago, where you see the all optical switching by femtosecond individual femtosecond laser pulses in a ferromagnetic rare earth transition metal alloy, gadolinium, iron, cobalt in this specific case. And you see how individual circular polarized laser pulse can switch opposite regions of magnetization in such a thin film. Now, originally, the idea was this helicity dependence was the key to the process, but later, actually, it was known that the basic phenomenon is already experienced by linear polarized laser pulses. And it turns out to be a toggle mechanism. That means if I fire successive linearly polarized laser pulses onto such a film, as shown here in a magneto-optical Kerr image, you start with a full single domain. A first laser pulse can switch a reverse domain, but the second one completely erases it again. And this process goes on and on in a toggle switching fashion. And it actually turned out that this original helicity dependence was just due to very weak circular dichroism, which you have intrinsically in such a ferromagnetic film. Now, to understand the processes better, we have to travel back in time, even by 10 years more. And around 1996, it was shown for the first time that using femtosecond laser pulse, you can really demagnetize a thin film at a hundredth of femtosecond time scale. This is here the pioneering work by Eric Beaurepaire and Jean-Yves Bigot, who showed indeed for nickel thin film, if you fire a laser pulse and you probe the magnetization magneto-optically by a second laser pulse, you see that the magnetization is quenched at a hundredth of a femtosecond time scale and then quickly recovers. And in those days, it was already recognized that if you want to explain such a process, you have to think of the interacting heat baths, heat reservoirs of the electrons, the lattice, and the spins, and how they exchange their energy and spins during the non-equilibrium process. Now, it turns out that the transition metal ferromagnets like nickel and iron and cobalt are all quite similar in their response. But if you take a rare earth metal like gadolinium, you find actually that the demagnetization profile is quite distinct. You see, you still have a relatively fast initial drop, but the full demagnetization now takes more than 2 orders of magnitude longer. On itself, it's an interesting topic, and I could spend half an hour talking about that. But for you, I just would like to ask you to remember the different time scales for the transition metals and the rare earth metals if we talk about this loss of magnetic moment after femtosecond laser irradiation. Now, the inside of the mechanism, the detailed inside of the mechanism for the all-optical switching actually was found in experiments in 2011 when femtosecond X-ray magnetic circular dichroism experiments were done by the group of Hermann Dürr. What you see here using femtosecond X-ray probe pulses after visible field pulses, which heat up the rare earth transition metal alloy. You see that actually you can in an element specific way, you can see the magnetization dynamics of the 2 sublattices. In blue, you see the gadolinium magnetic moment, and in red, the iron or the cobalt magnetic moment. And you see both of them rapidly demagnetize after laser excitation. But as we've seen before, the iron is faster than the gadolinium. And actually, interestingly, the iron really crosses zero. Then for about a picosecond, I have a transient ferromagnetic state. And then finally, the gadolinium also crosses zero. And if we wait now long enough, then the whole system returns to the original, but oppositely magnetized state. Now, by now, there's a big consensus in what the intrinsic mechanism is. First of all, we know from experience that actually the iron demagnetizes much faster than the gadolinium. But this means that once the iron is fully demagnetized, there's still a large magnetic moment in the gadolinium system present. Now, in this state, it turns out that exchange scattering, which can transfer angular momentum from the gadolinium to the iron and vice versa, becomes of extreme relevance. And it means that actually the iron can continue increasing its magnetic moment while gadolinium is demagnetizing. Thereby, we enter in this transient ferromagnetic state. Now, this clearly is not liked by the system because of the interatomic antiparallel antiferromagnetic alignment. And that means that actually also the gadolinium is pushed through zero, resulting in the final switch. Now, it is important to note that in order this process to work, one needs to be close to compensation, because there is a kind of subtle balance between the angular momentum which has to be exchanged. Now, in order to find more insight in this process, we actually started up some microscopic calculations using a so-called microscopic 3-temperature model. We start now with a microscopic Hamiltonian to describe the interplay of heat and angular momentum transfer between the electrons, the lattice, and now two subsystems of magnetic reservoirs. There is the 3D magnetic system for the transition metal and the 4f electrons, the 4f spins for the rare earth. Working out this model, it is important to mention two important interaction terms in this Hamiltonian. The one allows for dissipation of angular momentum, so to let the magnetic system thermalize. What we implemented it by means of Elliott-Davet spin-flip scattering processes, in which an electron scatters with a phonon, and then there's a finite probability that the electron flips its spin, thereby transferring angular momentum from the electronic system to the lattice. Secondly, and very important for the switching, there's the exchange scattering. In this case, we have both a spin flip on the 3D and the 4f sides, thereby transferring angular momentum while conserving the net angular momentum of the total system. Now, using this model, actually, we can easily calculate a phase diagram, as shown here, for the gadolinium cobalt alloy. Horizontally, you see the concentration X of the cobalt concentration, and vertically, you see the laser pulse energy. The blue area here is the region where you find the combination of concentration, cobalt concentration, and the laser energy for switching. And switching is only established in the model, like in experiments, over a range of a few percent around the compensation point at room temperature, which is indicated by the vertical dashed line. Now, to see what is actually mean and what is the origin of this phase diagram, it is interesting to have a look at the underlying time traces. If we go to a compensation which is close to ideal, close to the compensation point, but the laser intensity is not high enough, you see that both gadolinium and cobalt are demagnetizing, but do not reach the Curie temperature, and thereby both recover to the original orientation. If we increase the laser intensity, we see that actually now indeed cobalt fully demagnetizes faster than gadolinium, crosses zero. For about a picosecond, we have the transient magnetic state, transient ferromagnetic state, like in the experiments. And now gadolinium is pushed to zero, establishing the final switch. We can increase the laser energy even further. And what you now see is that you make the material completely magnetically dead for a long time, and then it spontaneously remagnetizes. And actually, this is it spontaneously remagnetizes into a multi-domain state. This is what is seen often also in experiments. If you see such a laser-written reverse spot, you see at the center a multi-domain state as a signature of this specific thermal demagnetization process. More interestingly, you can go to the optimal laser intensity, but increase the concentration of cobalt. What you now see is that there is too little gadolinium available to pull cobalt through zero due to exchange scattering, and thereby we do not end up in the transient ferromagnetic state, and thereby switching cannot occur. We can also go to a lower concentration of cobalt, and what then happens is that there's a lot of gadolinium, so cobalt can be easily pulled through zero. We do end in a transient ferromagnetic state, but there's now still so much ferromagnetic gadolinium left that actually it pushes back the cobalt magnetization, and thereby we return to the original state. And thereby we see all the different cases, and we understand why switching only occurs in a narrow range of a few percent around the compensation point. Now, let me now go to the next process, laser-induced spin transport, a next process which can be triggered by femtosecond laser pulses. The first glimpse of this was found by Gregory Malinowski when he was a postdoc in a group in 2008, and he performed experiments on multi-layered systems consisting of two series of cobalt-platinum repeats with perpendicular magnetic anisotropy, separated either by an insulating nickel oxide or a metallic ruthenium spacer. And he carefully measured the demagnetization profiles for both the metallic and the insulating spacer, and both for the antiparallel and parallel alignment. When he used the insulating spacer, he found that the demagnetization traces were completely independent on whether the two magnetic components were parallel or antiparallel aligned. If, however, he used a metallic spacer, he saw that the antiparallel case demagnetized faster, a little bit faster, and a little bit more efficient, as a sign that there is interaction, a spin interaction between the two layers due to the process of electron transport through the metallic spacer layer. Now, these kind of experiments have been reproduced by many different groups, and some of them you see here at the bottom. And there's also many different mechanisms by now available for which can lead to such a femtosecond spin transport. It would already arise if we have optically spin polarized electrons which ballistically are injected into a neighboring layer. There's an important and well-studied case of super-diffusive transport by the group of Peter Oppeneer in Uppsala, whereby spin filtering, you can inject also optically triggered spin polarized current into neighboring layers. But even if you just have thermal gradients in your films, also due to the spin-dependent Seebeck effect, you will have injection of spin from one layer into the neighboring ones. Now, there's an interesting fourth mechanism, and in that case, the spin currents are directly related to the loss of magnetization due to the ultra-fast demagnetization. And therefore, it is called the Dmdt mechanism. This mechanism can be easily understood in the context of an SD model for magnetism. In this case, the loss of magnetization in the localized D moments is via exchange scattering coupled to a build-up of spin angular momentum, spin accumulation in the mobile s-electron system. And having a gradient in the spin splitting of the s-electrons is readily a source for a spin polarized current. Now, doing models in an SD model, time resolved after optical excitation, you can readily reproduce the graphs like measured by Malinowski, as indicated here by present theory PhD students in a group, Martin Baines. You see, indeed, in the antiparallel case in blue, you have a slightly faster and slightly more demagnetization than in the parallel case. Now, you could say this is a bit of a boring case, because after a few hundred femtoseconds, the system gets back into equilibrium and then the two traces are identical. But this changes if we go to a non-collinear alignment of the generation and injecting layer. Also, this has been investigated by different groups. Again, some other results are listed here at the bottom. Here are some experiments from Eindhoven, where we use a generation layer of a cobalt nickel 4 repeats with perpendicular magnetic anisotropy. A femtosecond laser pulse demagnetizes this cobalt nickel ferromagnet, thereby produces a source of mobile s-electrons, which are injected via a spacer layer of copper into a top layer of cobalt with an in-plane magnetization. Now, just like in spintronics, we now have a spin transfer torque exerted on the top magnetization. The spin is very easily in this non-collinear configuration. Spins are very efficiently absorbed and give rise to a canting of magnetization just to conservation of angular momentum. What we finally see is that this canted state gives rise to a ringing of a magnetization in the next hundreds of picoseconds, which can easily be probed by a second magneto-optical probe pulse. Also note that if we reverse the magnetization of the bottom layer, of course, we have rather than an upward scanting, we get a downward scanting, and you see indeed that the oscillations are changed by 180 degrees, as expected. So thereby we have the two concepts which will be of relevance in the rest of this presentation nicely explained. The next step is to go to this hybrid devices where we want to exploit both all the spintronic tricks as well as the all-optical switchings. And we would like to, therefore, to have the all-optical switching being present in synthetic antiferromagnets. Now, after a couple of failures, actually we came up with this very simple system. What you see is a tri-layer platinum cobalt gadolinium, where the platinum cobalt interface, the combination of a ferromagnet with a heavy metal, gives rise to all the important spin orbit effects, like the perpendicular magnetic anisotropy, the DMI, and the spin Hall effect. While it is known that gadolinium in contact with cobalt gives rise to an antiparallel coupling of the magnetization in the gadolinium and the cobalt. Unfortunately, gadolinium has a Curie temperature just below room temperature, and certainly in very thin films it will even be lower. Nevertheless, due to a proximity effect, one expects a very thin layer of gadolinium ferromagnetically aligned antiparallel to the cobalt at the interface. Now, if you grow these kind of films, you can easily demonstrate that it is indeed the alignment. You can measure using magnetometry, in this case VSM squid magnetometry, the magnetic moment as a function of temperature when you cool down from room temperature below. And you see that cooling down, first the magnetization goes down until you have zero magnetization at a compensation point, and then finally the gadolinium magnetic moment starts to be the dominant component. You can analyze these traces, and then you'll find that the saturation magnetization at low temperatures is about 1.8 megaamps per meter, very close to bulk values for gadolinium. And moreover, you find that indeed there's a very little bit of gadolinium in the ferromagnetic state, proximity induced at the interface, no more than effectively 0.4 to 0.5 nanometer. And the question is this enough to give rise to the all-optical switching? Well, it turns out to be actually kind of an ideal system. And the switching here is extremely robust. If you just take this film, you grow it, and again, you do magneto-optical microscopy after focusing a laser and firing successive laser pulses, indeed, your first laser pulse writes a nice circular domain, and the second one erases it again. And this process goes on and on and on. And actually, you can do this at 100 kilohertz and keep the laser firing for an hour, and even after billions of pulses, you have no failure. Everything is reproducible, and this is a highly robust toggle switching scheme. Now, not only is it super robust, it is also ultra efficient, as shown in this next experiment. A very simple experiment. You just now take again your film of platinum cobalt gadolinium, and you fire laser pulses of increasing intensity, of increasing pulse energy. Initially, nothing happens, so there's a threshold fluence, but beyond a certain fluence, you see that you write a domain, and the domain becomes bigger the larger the intensity in your laser pulse, the larger the energy in your laser pulse. You can now plot the intensity as a function of, you can plot the domain size as a function as pulse energy, and you can fit it assuming that everything is a local process and that there's a very specific threshold energy locally. And this compares a little bit this experiment like having an iceberg, and you measure the area which is above the sea level. And if you know the shape of the iceberg, you know how much the domain will grow, the region above sea level will grow if you raise the iceberg. That means from such a fitting as we can do, which is quite perfect, we can now transfer this pulse energy to a fluence, and actually we'll find that this corresponds to a threshold energy of 50 femtojoules if you would have a domain of 50 by 50 nanometers squared, as you might ultimately want to have your bit size. So actually, this is a very competitive energy if you compare with all kind of present days spintronic switching energies. Moreover, you see, if I increase the amount of cobalt, increase the thickness of a cobalt, the switching energy goes up, but nevertheless, we still establish all optical switching. And you could wonder what happens if you can keep on continuing the cobalt layer thickness. Now, if we continue the growing thicker films of cobalt, you will find that the perpendicular anisotropy is not strong enough anymore to keep the film out of plane, but you can grow now cobalt nickel repeats, and therefore much more ferromagnetic material still have a PMA orientation. And you see that indeed the threshold fluence, which is plotted here as function of transition metal layer thickness, keeps on growing. But still, even after reaching 5 nanometers of cobalt nickel, we still have a all optical switching threshold fluence. And this is actually quite amazing, because for the alloys, we found that actually we need to be pretty close to compensation with a few percents. And here we can tune the thickness of our transition metal layer thickness by a factor of 10 and still do observe switching. So in itself, that's a fascinating observation. Now, how come? Well, in order to explain, we went back to the drawing board, and actually we extended our calculations from the alloy case, from a disordered alloy, to a layer by layer ferromagnetic system, where we have first layers of cobalt, and on top of that, layers of gadolinium. What is plotted here now is the number of cobalt layers if we keep the number of gadolinium layers fixed to 3. Switches perpendicularly indicated along the y-axis is again the pulse fluence, and what you see in blue again is the region where I get all optical switching. You see, indeed, if we increase the number of cobalt layers, the threshold fluence goes up, but still, even up to 20 monolayers of cobalt, also in the simulations, we do establish switching. So unlike the alloy case, where we could only change the amount of cobalt by 5%, here we can change the amount of cobalt by 500%. Now, how come? Again, we go back to the underlying time traces. What you see here now is a layer dependent, the magnetization in successive layers in the gadolinium cobalt stack. The blue colors are all referring to the gadolinium, and the red and orange colors are referring to the cobalt layers. You see that on average, indeed, the gadolinium rapidly demagnetizes, and there is a transient ferromagnetic state for some time, and then it reverses to the other side. And the gadolinium, you see some nice details. For instance, you see that there is a strong difference between the magnetization in neighboring gadolinium layers. Of course, this reflects the fact that it's proximity induced. The layer closest to the interface has the largest magnetic moment, and then layer by layer, the magnetization goes down into the gadolinium. Now, if you want to see what's happening near zero, we have to zoom in, and then it becomes clear that all the different cobalt layers do not cross zero at the same time. You see that the layer closest to the interface, which is the dark red color, crosses first, and then the next and next and next. So actually what we have, that we have a first switch nucleated at the interface, and then a propagation of a propagation front of reverse magnetization, which propagates into the cobalt. And in some sense, you could say that's not so strange, because the switching itself is driven by the angular momentum interchange at a cobalt gadolinium interface, and therefore it has to start there at the interface. And the rest just, it can carry this information into the rest of the cobalt, and therefore it is kind of so robust, and you're not sensitive on the concentration, because this initial nucleation will always occur. Now, finally, of course, you would like to have some time resolved insight. Now, and interestingly, I will not be going in too much details, but you can now again use this highly robust toggle switching, because in principle, the toggle switching is a kind of annoying if you want to do pump probe stroboscopic experiments, because we switch down and up and down and up and down, and if you measure a time average, we will see nothing. But we realize that we have odd pulses, which are always switching in the one direction, and the even pulses switching in the other direction. And since this whole process is so reproducible, we can keep our laser running for up to an hour, and we just electronically gate either the even pulses or the odd pulses. And you see for the odd pulses, you nicely resolve here the switch from up to down in a few picoseconds, and then a full converging of the magnetization in the opposite direction in the next hundreds of picoseconds. And for the even pulses, we see the reverse effect. Now, you could also have done this experiment by applying a magnetic field, and thereby in between two pump pulses, let the magnetization in a field-driven manner reverse to the original state. But actually, at some point, you will see that actually the magnetization is going to change your time profile. You can also measure that explicitly. So here you see now the same experiment, but now in a magnetic field. And then you see that at low magnetic field, it takes a long time before the magnetization will recover to the original state. But if I apply fields of above 100 millitesla, I see that the recovery to the original state already sets in after about half a nanosecond. Now, on itself, that is interesting because this is, you could say, kind of surprising, because we know that this switching is exchange driven, so actually driven by fields of 1000 Tesla. So how come that we can already reverse the magnetization after hundreds of picoseconds, while these magnetic fields we apply externally are only 3 or 4 orders of magnitude smaller? Well, actually, after doing some further thinking and some additional experiments, we came to the following picture, that indeed this switching is a longitudinal process driven by exchange. Then this back switch is more a precessional phenomena, where magnetization is precessing into the other original direction and converging due to Gilbert damping. While at a longer time scales, also domain one motion plays a role. You can write a small reverse domain, and then before the next pulse, actually the domain has collapsed due to domain one motion. Now, the final example which I want to show of all optical switching is one where actually several of the ingredients are not going to be combined. And actually what it will show is that we can enhance the all optical switching by optically induced spin currents. For that, we designed the following system. And when I say we, I mean Yuri van Hees, a present PhD student in a group, and his co-workers. And we have, again, a bottom spin generation layer of cobalt nickel. We have a transport layer of copper. And on top of that, we now have our cobalt gadolinium bilayer. Now, this generation layer, what it does, if we are firing a laser pulse, we will generate spin currents, which can be deposited into the cobalt. And we have a nice interplay of transfer of angular momentum. First of all, of this, let's say, spin injection from the generation layer, but also the spin injection from the gadolinium, the spin exchange between the cobalt and the gadolinium. And now one would expect that one can assist the all optical switching if the spin current injected from the cobalt nickel has the same orientation as that of the gadolinium. Whereas we could hinder the all optical switching if the two have the opposite orientation. To probe this, we can do again the very simple experiment, measuring the domain size as a function of laser pulse energy. And we can do it now for the antiparallel and the parallel starting state. Indicated here is the graph for a antiparallel first state. And if we do it for a parallel, indeed, we see that the threshold fluence is about 20% larger. So that means that indeed, starting in an antiparallel fashion, we have a more easy switch than in the case of the parallel one. Now, this is a nice demonstration of competition between two different spin transfer sources, but it is also of relevance for generating functionality. Because you might have wondered, hey, it's interesting to have this toggle switch scenario, but if you have a toggle switch, you cannot deterministically set it to a specific value. And actually, using now these two different threshold fluences, one starting in the antiparallel case and the other in the parallel case with respect to a reference layer, allow you to generate deterministic schemes. Let's have a look. We fire now a laser pulse with intermediate power in between the two threshold fluences onto two magnetic states, the one in the antiparallel indicated in the MOC image here in dark color, the other parallel is the light color. If we absorb this laser pulse with intermediate energy, we see a reversal in the case of the antiparallel state, but no reversal in the parallel one. We could now fire a second laser pulse, which has a higher intensity above both threshold fluences, and then it will always toggle switch. So it means that having this as a second pulse, we see that the central area always will reverse. And if we now encode dark area by 0 and light area by 1, you see that only the intermediate single pulse will always set to one state, whereas the two successive pulses with different energy, one below and one above the highest threshold fluence, will always set as 0. And thereby we have transferred the toggle switching into a deterministic switching, making being assisted by this reference layer. Okay, then in my last slides, I would like to give you a kind of update of the last experimental steps which have been performed, which hopefully brings us closer to a kind of using all these novel handles on magnetic materials for future applications. The first thing which we have to demonstrate is that indeed our synthetic antiferromagnetic systems are not kind of ideal systems for optical switching, but also give rise to the ultra-high current-induced domain wall velocities. Now, in order to more easily get compensation at room temperature, rather than a bilayer, where in principle it's also possible, but it's a bit more difficult, with a quad layer, cobalt, gadolinium, you have more interfaces, and thereby the ratio of gadolinium to cobalt magnetization is different, and we can bring them to compensation at room temperature. We make a strip out of that, and we nucleate a reverse domain and send laser pulses through, and you see 1 pulse, 2 pulse, 3 pulse, 4 pulses. You nicely see that the up, down, and down, up domains move in the same direction, as indicative for spin orbit torque driven domain wall motion for chiral domain walls. And at the right domain, at the right figure, you see that actually we measure now the domain wall velocity as a function of current density. And indeed, you see in this case, we reach 1500 meters per second, but now we have, with the proper samples, we reach now velocities above 2000 meters per second, and verified that all these structures are optical switchable, independent of the respective layer thicknesses. So we have the ideal system for these kind of hybrid approaches. Now, in order now to have the all optical switching and the current induced domain wall motion represented in the same experiment, this is somewhat older data where we didn't find these high velocities yet. So this is still in the creep regime, but as a proof of concept, it is a nice example. You see that we now make a strip again of the material. We fire our laser pulses somewhere here downstream, while having a DC current present in our strip. And you see all the written domains are immediately carried along with the flow of electrons to downstream, where we electrically detected by a Hall cross over there. We now plot the anomalous Hall effect signal as a function of delay time, where the vertically dashed lines are the moments that we fire the laser pulses. And you see always a little bit later, we see the two domain walls passing our second detection station. So showing that indeed we can combine the two functionalities nicely in a single device. Now the final step would be to embed all of this in an integrated photonic chip. And there we teamed up with colleagues from the electrical engineering department, in particular the group of Jos van der Tol. You see one of his PhD students, Sander Heiniers, and one of our PhD students, it's Dmdt. They make these kind of photonic devices. And we zoom into a special one, which I will describe in more detail in the next slide, where we have now on one of the branches, we have an ultra small cladding 300 by 4 nanometers of our PMA material. And we're going to measure its state by optical pulses, which are fed in by grating couplers and read out by grating couplers. Now, a cross-section of this photonic device, which actually is based on indium phosphide waveguides, is indicated over here. We see here the waveguide, we see the mode profile, and on top of that, we see our ultra-thin magnetic cladding, which we have deposited and structured on top of the waveguide. Now, you see here what is happening in such a device if, for instance, light in a TE mode is propagating through the waveguide. Due to the presence of this small island, ferromagnetic island on top of it, we will be getting magneto-optical effects whereby a small orthogonal TM component is being generated. Now we have a triangular section where the eigenmodes for propagation are rotated, and having twice a projection of the original modes into the triangular section and back to the rectangular mode, we transfer the polarization effects into intensity effects, which we can measure either by detecting the TE light or the TM light exiting our device. A typical example is indicated here when we now measure the hysteresis while scanning the magnetic field and measuring the intensity in either the T or TE or the TM channel. We see that we at the moment have up to 2% of intensity change just from this very small magnetic island, only 2 nanometer thick here on top of the waveguide. 2% is not yet too much, but we're working on all kind of ideas to enhance the signal using plasmonics and maybe using other kind of tricks whereby we get to more useful intensity modulations. Okay, having discussed with you also our attempts to get closer to integrating all of this really in the photonic integrated chips, I'd like to come to the end of this presentation. As a kind of take-home message, I hope you are convinced indeed that these fields of femto-magnetism and spintronics are rapidly progressing, and it's a nice interplay of all optical switching and optical spin currents. But moreover, it may indeed be a route towards new integrated magneto-photonic devices. Now, as a kind of final gadget, you see here this animation, and you may understand what it is. We now have 3 laser pulses, which are fired after having displaced the laser focus a little bit. A nice reflected is a toggle behavior. If you expose an area twice, you go from light to light to dark. But moreover, it is not an arbitrary pattern. Actually, it is the logo of our Institute for Photonic Integration. And we claim this is the fastest logo ever written because we wrote it in only 300 femtoseconds of time. Having said that, I would like to thank once more all the bright young researchers, supporting staff, and colleagues at the Eindhoven University of Technology. I would like to thank Jaru once more for the invitation and for the great bottles of wine and the Christmas card, which has safely arrived. And I would like to thank all of you for your kind attention.
Thank you very, very much. Wonderful talk. As always, never disappointing to hear from you. So we have now a few questions. Of course, please raise your hands and then I'll give you the floor. Michael, why don't you unmute yourself and start the round of questions?
Yes, thank you, Jai. Thank you, Bert. It was again a pleasure to listen to wonderful physics. I'm coming from a different direction, looking at magnetocalorics. So now you have the option of having gadolinium films in exchange with the cobalt, so not an alloy, but truly gadolinium layers, which should show a magnetocaloric effect of 10 to 12 degrees at the phase transition. So I wonder, how fast is the entropic change of the alignment of magnetic moments and misalignment transferred to the phonon bath and back? As you do that, you change the temperature essentially.
Yeah. So in a sense, you are talking about the heat capacity of the magnetic system.
Yes.
Well, and you're particularly talking about the gadolinium, or?
Yes, just the gadolinium because it has the biggest effect.
Yes. Well, in the sense that those effects are not dramatic, you could say is indicated by the fact that for the transition metals you can have switching down to 50 femtoseconds. Indeed, gadolinium is much slower, and you could say in a sense we are profiting from it here because it is an essential ingredient that you have your 2 reservoirs which are aligned in an antiparallel.
Bert, sorry for interrupting.
Yeah.
I'm thinking from a completely different side.
Yeah, okay. Yeah.
How efficient could you make a magnetocaloric cooler on the femtosecond scale by switching the magnetization, for example, on this scale?
Yeah. Oh, yeah. I never thought about it like that direction, but of course it could be interesting because you can relatively quickly switch it. But you mean just demagnetizing and magnetizing, crossing
exactly. And then you need to find a way to transport the heat away for each switching process.
Well, that's interesting. So because there are other reasons why we want to transport the heat quickly away, and we are engineering the thermal properties of these stacks, for instance, by having metallic films which absorb a lot of heat but are not heated by the laser in close proximity. And that is also needed if you want to, of course, what I showed here is one switch.
Yeah.
If you want to go to high data rate, you want to have a next switch as soon as possible. But that means that you have to, let's say, suck out the heat as rapidly as possible. And what we have shown is that experimentally, that is work in progress, but we have a preprint on that topic, where actually we show that after 10 to 20 picoseconds, we can have a second switch.
Mm-hmm.
If we are able to cool down the system quickly enough.
Okay.
So that means that you can cross the phase transition point pretty rapidly. What it means for cooling power, I have not the faintest idea, but maybe you can come up with that solution.
Yeah, but the combination would give you intrinsic cooling at the same time.
Yeah, but yeah, but of course you should also see then basically how efficient it is, because you still, of course.
Sure.
But yeah, that's a calculation that can be done. Yeah. Okay. Interesting idea. Yes. Yeah. Thank you.
Okay, great. So thank you. Let's go next with Jörg. Go ahead. Unmute yourself and ask your question.
Yes. Very nice work, Bert, and nice to see you online. In principle, you have already answered half my question, because I was thinking about if you can do switching at femtosecond time scale. I mean, you can only use the time scale if you can do something after very short time. So you said now that after 20 picoseconds, you can do a second writing. Actually, how fast or how short is the time that you need to wait before you can do a reliable readout when you do switching?
Yes. Well, that answer depends on what you, of course, time resolved experiments are done at a femtosecond time scale. So basically, if you have a laser pulse, you can read out at any moment. Of course, if you are referring to the device which I've shown, where we use the magneto-optical effect, then of course you have a relatively small magneto-optical effect, and you need enough integration time. I would say that is work in progress. So basically, we make some estimates. If you would have, if you would read out with 1 milliwatt of light intensity, I think if short noise would be the limit, you certainly could make it to gigahertz data rates. But I would say I would not basically keep away from it a little bit, of course. But of course, it's a very relevant question.
Yeah, because I mean, gigahertz data rates, that's something that hard disk can do nowadays.
Yes. Yeah, but of course, I mean, I would say I would not see this as a replacement of our present days memories. But what you could do, if you could, for instance, write at basically you have incoming photonic data at an extremely high data rate, and store all of that without any intermediate electronic steps directly into a memory. So basically, the application of that will be different than basically what we have as a random access memory, where you are writing bit by bit.
Okay, that makes sense. Thank you.
Great. Sanjita, go ahead and unmute yourself and ask your question, please. We don't hear you. I don't know if you're the...
Can you hear me now?
I can hear you. Yeah, perfect.
Thank you. Bert, that was really nice talk. Thank you very much. I have a question regarding the switching. There are two kinds of spin excitations possible. So you can flip the spin, or you can rotate the spin between, for example, gadolinium and iron. What is the relative contribution of the two? And can this be tuned? Is this time dependent, the relative contribution?
Well, the honest answer is I do not know. And in the simple-minded description we have, we do not describe the rotation of this. You would need, I mean, if you do it quantum mechanically, so you need to have superposition of states. So we do not answer that. What I do know is that, of course, you can also work this problem out using, for instance, atomistic LLG calculations, where you have the LLG equation operating at atomic scale. And then, of course, what you're talking about is the rotation of magnetic moments. And typically, the outcome is surprisingly similar with what we find. because that also in that, of course, in that case, you have rotations of spins, both on the rare earth side and on the transition metal side. But the time scale set by that is exactly the same thing, where basically we use a more Weiss-like picture of up and down spins, because the energy scales are the same. So how to distinguish between the two, let's say in an experiment, I do not know, but I would say there are different theoretical approaches, one focusing on the one picture, one on the other, but actually you see that they're converging with respect to what they predict.
Yes, okay, thank you. Thank you.
Excellent. So Sumit, if you could unmute yourself and ask your question, please.
Sure. Hi, Bert. Thanks for this nice talk. So I have a rather simple question. When you are doing optical switching, as I understand, you're supplying angular momentum through your laser, right?
No, that was the original idea. That you use circular polarized laser pulses, and then helicity dependent you can switch. That is indeed possible, but the effect is much more subtle than what we see. So with helicity independent switching with linear polarized light, you do not dump angular momentum from the laser field, but you have basically you use the sudden heating to have ultra fast exchange of angular momentum between the two components. I
see. So in that case, the angular momentum of light doesn't play much role in the switching.
So the original work from the Nijmegen group on the switching of the gadolinium iron cobalt, there was an helicity dependent effect. At the end, it turned out to be only a minor change of the threshold fluence by maybe 5 or 10 Kelvin, which triggered those effects. We also tried to measure for our bilayers. In our bilayers, we do not measure any helicity. By symmetry, there should be a little bit of diagorism, and thereby there should be a difference between the different types of helicities, but it's immeasurably small, the difference for us.
I see. And then if I go to your slide number 13, where you show the dependence with the strength of your laser.
13 or 30?
13, 1, 3, where you show multiple phases of this cobalt gadolinium cases. Yes. So in this case, if I give the same strength of laser and increase the pulse width, would I see the similar effect then?
That's very interesting. As long as the laser pulses are sub-picosecond, you do not see too much. So basically, there have been groups in Nijmegen, also in Berkeley, Jeff Boker, for instance, who have investigated, also in Nancy, who investigated that in much more detail. What you see is, as long as it stays sub-picosecond, nothing changes much. But then you see, you can stretch the pulses up to about 10 to 15 picoseconds, and then you see the margin between all optical switching and ending up in this multi-domain states are getting smaller and smaller, because once your system is no longer in a non-equilibrium state, then the switching is not possible anymore. So the maximum pulse length is of the order of 10 to 15 picoseconds. But then you see that the margin between the all optical switching threshold and the multi-domain threshold is getting very small.
I see. And in that case, does the frequency of the laser play any role?
You mean the wavelengths of the repetition?
Yes.
The wavelength.
Yeah.
No, the wave that has been much more investigated in the case of demagnetization. In the case of demagnetization, I think the present, well, I would say consensus, at least my belief is that doesn't play a role. There's also studies using terahertz electromagnetic radiation, and they see exactly the same time scales. So it's just the electromagnetic field a large part of the process is just dumping energy into the electronic system by the electromagnetic field. Of course, there will be subtle effects, and depending on the system, you might more or less profit from that. But a large part, I'm convinced that a large part is just thermodynamics, that the laser allows you to very rapidly heat up the electron system.
I see.
Although it is not everything.
Okay, thank you.
Excellent. So Sasha, you're next.
Yes, hello. Thank you very much for a really interesting talk. I have a question about this switching structures where you have a platinum layer. So when you mentioned that when the structure doesn't have any more the perpendicular magnetic anisotropy, so when it gets in plane anisotropy, then there is no switching. So do I understand correctly that it's really it doesn't switch, or it's just you cannot observe the switching because the magnetization is in plane?
No, sorry. From practical point of view, if you continue measuring in the same configuration, you will not see any switch. There is some scattered evidence, as far as I know, and we have also some scattered data that there's no reason why it would not switch if it's in plane.
Okay, thank you.
Martin, you have a question?
Hi, Bert. Thanks very much for your interesting talk. I have a question regarding cobalt gadolinium. This deterministic switching versus toggle switching. It cannot be the same mechanism. I was a little bit confused how you explained the difference in the mechanism between these two, let's say, ways how you route and how the magnetization compensation point plays a role. That was also not quite clear.
So now, which slide or which?
It doesn't play a role. What is the difference in the mechanism between toggle switching, what you explained with the transient ferromagnetic alignment, which cannot be the mechanism in deterministic writing?
No, but the thing is, so basically, in this case, it is still toggle switching. But the toggle switching, you have only exchange of angular momentum between the cobalt and the gadolinium. Now we have a reference layer, the cobalt nickel, which also can add angular momentum. And if this additional angular momentum coming from the cobalt nickel has the same polarization as the angular momentum coming from the gadolinium, we help the switch. Whereas the angular momentum coming from the reference layer is opposite to the magnetization of the gadolinium, it will hinder the switch. So you could say it's still toggle switching, but toggle switching together with a net spin injection.
Okay, yeah. And you also mentioned that it's important that we are close to the magnetization compensation temperature. Why?
You mean for the alloy?
Yes.
For the alloy, well, what you see, experimentally, that is what is found. And if we do a modeling, it is exactly like I mentioned. If we have the percentage of cobalt too high, you see that there is not enough angular momentum provided by the gadolinium to push cobalt through zero. You can easily imagine if there's no gadolinium, cobalt will never cross zero. So you have a minimum amount of gadolinium needed to cross it through zero. If
you mean it just depends on the ratio between cobalt and gadolinium, that the net magnetization is close to zero, does not play a role?
Well, you see that, I mean, you have to be roughly near compensation. Apparently then it is most then the exchange of angular momentum is most efficient, but it's clear the limits that you are far above and far below, that is clear what is there happening. So if the amount of cobalt is too large, then you see there's too little gadolinium still to add enough angular momentum to have cobalt crossing zero. And if the amount of cobalt is too low, the cobalt very easily crosses through zero, but then the gadolinium has hardly demagnetized, and then you should completely reverse it, and then actually you see that the gadolinium becomes the stronger magnet, which pushes back the cobalt, and that is basically what can be easily read out from the simulations. I'm not sure whether I make myself clear.
Yeah, I see the point. Yeah,
Matthias, when you would like to mute yourself.
Yes. Thank you. So first of all, you have a wonderful talk. Thank you a lot. I have like one physics question and one technical one. So the physics is maybe very short. So as I understand it, it's crucial here to have the two different sublattices in these synthetic antiferromagnets with different Dmag times.
Yes.
So does that mean that this fundamentally cannot work in a true antiferromagnet?
No, but I think that it doesn't work in a true antiferromagnet. I would say is Well, maybe it's not based on symmetry, but it's very difficult to get a toggle to work. It's completely symmetric because there is no directional effect anymore because you heat it up. I think it's certainly this mechanism is not going to work.
Okay.
Because you need basically still one magnet with a magnetization, which by exchange scattering can draw the others to zero.
Exactly.
But of course, with two the same ones, you end up in zero, close to zero, and the game is over.
Yes, exactly. This is what I mean. Okay.
Yeah,
and then the technical thing is, so you said that you have amazingly low switching energies, these 50 femtojoules, something like that, right? Yeah. But I think what's crucial in the end is really the energy that you need for the device, which will include the generation of these femtosecond pulses.
Yes.
So can you comment kind of like what is needed in terms of development from the laser side to make this really kind of like low energy competitive?
Well, the two things. One thing is you rather would not like to use femtosecond pulses, but rather maybe if you're talking about photonics. Photonic chips, you would like to have, let's say, pulses of several picoseconds or maybe 10 picoseconds or whatsoever. So from that point of view, it is promising that you can still have some all-optical switching with 10 picoseconds, but then you can make an estimate. So basically, if you have the ultimate application would be that the energy already carried by the data bits in the photonic domain provide enough energy to have the switching done. And we are not that far off.
Okay.
And of course, you can tune a lot of parameters. Actually, by playing around just with the optical environment, we have some simple things like playing with dielectric layers. We have pushed the switching fluence already down to 15 femtojoule. Then just you increase the absorption. We are now working on plasmonic photonic simulations using plasmonics, where you can locally, basically, you have a certain pulse energy, but you focus it onto a spot of 50 nanometers, having again an amplification of, say the local temperature. So in a sense, I would be rather optimistic that at least in an experiment you get it working with laser energies which are compatible on an integrated device. I mean, whether at the end you can handle all the complexity and come to a high data rate and a massive storage device, I mean, that is something else. But I think the individual devices should certainly be realizable.
Okay, thank you very much.
So Gernot, if you could ask your question, please.
Hi, Bert. Great stuff you presented. So you caught up with the velocities due to the current-induced domain wall motion. But in that case, in the racetrack type motion, there is a lot of power dissipated and the heating is severe. Yeah. Can you guarantee less power or heating effects?
Yeah. Well, a very good question. So we have one argument. What certainly will be energy efficient is the fact that in this scheme you do not necessarily need high frequency electronics, which go nowadays as, let's say, the biggest source of the energy consumption. But of course, if you want to have a steady flow of your domains, you would need to be able to drive a current for a longer time, where typically you also get a lot of heating problems. Mm-hmm. So that certainly will not be an easy task.
Okay. So then when you have the current assisted motion, yeah, then are these high density currents or is that less?
You mean our plots on the velocity?
Yeah.
As a function of let me what was it, this one here? These are nanosecond pulses of typically 10 to the power 8 amps per square centimeter, so 10 to the power 12 amps per square meter. Okay. So I mean, in a sense, this is not, I mean, the fact that we measure these kind of velocities for such kind of structures, of course, that is well known now in our community. But the nice thing is that basically you can demonstrate that the same films, which are highly efficient for the optical switching, also show these record high velocities.
Okay.
Intrinsically, there's nothing new about this stack, about this slide.
Okay.
Although, of course, what remains nice, I mean, there's all kind of the fact that this cobalt gadolinium interface, you could say, is so efficient for optical switching, makes engineering extremely simple. So basically, you can add, I would say, whatever we add, it also switch. Okay. And of course, cobalt gadolinium is not advantageous because it has a low anisotropy, so it will be horrible for making small domains. But you can also make a tri-layer with terbium, and then it still switches optically, and then you have a high anisotropy. So there's a lot of engineering possibility by adding layers, and then you see that typically you can add, well, kind of whatever you want, and it still switches.
Okay, thank you.
Great. And the last question from Igor. Can you go ahead and mute yourself and ask the question, please? We don't hear you.
Thank you very much.
Okay, go ahead, Igor.
Nice presentation. I have a couple of questions. One is about size dependence of domain on fluence. And the question is whether it's somehow sensitive to temperature, to initial conditions, or maybe temperature, of course, moves from compensation point, but can it be compensated by fluence or not?
Yeah, of course. I mean, if you would start the experiment at the temperature, of course, the amount of heating needed to reach the Curie temperature will be different. The compensation point might lie somewhere else. So basically, that would also mean different switching. But you could say the nice thing for the.
Yeah, here's Günter Roth.
Okay, sorry. Somebody's. I think
again.
Now it's okay.
No, not good. Yes, yeah.
That's okay.
So I would say basically, I would imagine that the temperature effect is causes more problems with the alloys than with the bilayers. Because with the alloys, if you start in a different temperature, you will have a different compensation temperature, and you might something which initially switched will not switch anymore at elevated temperature. If you have the alloys, you are much more insensitive to the amount of gadolinium and cobalt magnetic moment, and thereby you will be more inert. Mm-hmm. Okay. But I'm not sure whether that answers your question.
Well, partially yes, but okay. Another question is what is the decisive factor for speed? You mentioned that even 5,000 meters per second can be achieved, and in another example, 2,000. Yeah. So what is the decisive factor for motion such a large speed?
Yeah, maybe I should ask other experts in the audience who come up with a more decent answer. I mean, I know that basically for difficult parameters, this is also what you can get from simulations, that this is feasible. Of course, you're helped by the exchange between the layers plays an important role, and therefore also the cobalt. Let's say if you compare with the synthetic antiferromagnets with a spacer layer like ruthenium emitting, usually you have your smaller exchange, and you might earlier hit limits. But I mean, yeah, it's a matter of engineering. But basically, which of the parameters is stopping you from going an order of magnitude higher, I should look back at the equations.
But you mentioned about experiment with terbium, or probably with any other rare earth which has non-zero orbital moment. Did you notice any difference in speed?
With domain motion, we didn't study terbium.
No.
With the domain motion, we didn't study terbium, but I know that there's results on terbium with domain motion around the compensation point, so that works. For optical switching, terbium is also for the alloys, but also in the bilayers we find that terbium is more difficult than gadolinium. But like I say, of course, you can also work with combinations of cobalt, of gadolinium and terbium, and use the one for the switching and the other for the high anisotropy.
Okay. Thank you very much.
Thank you. Let me thank everybody, the 160 of you that showed up. Thank you, Bert, for a wonderful talk and answering all the questions. And being the last one before Christmas, I would like to share with you, I hope you guys have seen the Christmas card from SPICE to wish you all a very safe and healthy Merry Christmas and a Happy New Year to all. And we will see you in January in the next continuation of our talks. So with that, I'm going to hang off later. Where I need to stop the streaming here. I just finished the streaming, so we finish the thing.